Welcome back. So in the last segment of this lecture, we looked at selection sort, a big O of n squared sorting algorithm. And now what we're going to do is look at a different type of sorting algorithm in this segment. And then the next segment, we'll do the code and the runtime analysis. And we'll do that for a couple more times, getting a sense of the landscape of different types of sorting algorithms and their runtime complexities. This sorting algorithm is called insertion sort. And for simplicity, I'm going to, again, just work with a small list and assume that there are just integers in it. But again, it can be anything that can be sorted alphanumerically or according to some key. So, like selection sort, insertion sort is an iterative algorithm. And on each iteration, we are going to ensure that the first nth items are in sorted order. So on the 0th iteration, we are going to ensure that the first item in the list is in sorted order. Well, there's only one item in that list, so of course it's in sorted order. So let's go on to the next iteration. So at iteration 1, I want to make sure that just these two items are in sorted order. So what does that mean? Well, there's only one item here, so that is by default in the right place. Now this item 2, we can see, is less than this item. And again, we're going to sort this in increasing order, but of course we could have done it in decreasing order by just flipping everything. So since this item here in the position 1 is less than what's in position 0, I'm going to slide it over, and then I'm going to insert it, hence the term insertion sort. So now notice that after the first iteration, 0 and 1 iteration, these two items, ignore the rest of the list for now, are in sorted order. They're exactly right, 2 followed by 5. Now, on iteration 2, we're going to repeat. So we pull that item out, 4, and we're going to slide it leftward until it's in the right order. Now notice that as I slide it leftwards, once I know, so I slid it this way because it was less than 5, of course, and at this point, I know that 4 belongs here because it is greater than 2, and everything to the left of 2, there's nothing there, but if there were, must be in sorted order because we assumed everything there was in sorted order. So we can drop 4 into there. And now 2, 4, 5 at position 0, 1, 2 are in sorted order. And now we can repeat the process. And notice that the reason why this works is that as I take an element and slide leftward, as soon as I hit an element that I am greater than, well, that's its home because everything to the left of that is already in sorted order. So we pull the 6 out. Well, 6 is greater than 5, so it just goes right back to where it belongs. It can't belong anywhere over here. Now the first 4 elements are in order. We pull out the 1. We ask, is 1 less than this item? Yes. Slide it down 1. Is it less than this item? Yes. Slide it down 1. Less than this item? Yes. Yes. And now we found our home. And again, the first now from 0 to 4, the first 5 elements are in sorted order. And now we just have to do the last element. So again, compare it to who you're next to. It's less than, it's less than, it's less than. At this point, it is greater than, which guarantees you that it is greater than everything to the left of that because all of these items are in sorted order. And so we insert the 3 into the list. That's it. Pretty simple algorithm. Here's a nice exercise for you. Write insertion sort. It should be about 10-15 lines of code. In the next segment, I'm going to show it to you, but it's a nice, simple exercise for you to do. And think about what the algorithm is again. It's an iterative algorithm. On every iteration, you take the element at that position, and you keep sliding it leftwards until the item to its left is greater than it, in which case you have found your home. Okay, so try that out, see what happens, spend a little time on it, and then when you come back, we're going to look at the code and we're going to do the runtime complexity. Okay. See you in a bit.